All right, so it's my great pleasure to introduce Polo Chow to Microsoft today. He's going to talk. He's an associate professor at Georgia Tech, got his PhD at Carnegie Mellon, and he's got some famous papers, the Polonium papers, like the ones I know have read definitely in detail. And today he's going to talk to us about mining research papers and patents and product descriptions for great ideas. So,
okay. Yeah, thank you, Jay, and also everyone in attendance and also joining us remotely. So today I'm going to talk about two related topics. One is how to make AI more secure, and then the other is how to make AI more interpretable. So at the first glance, you may think that it may not be directly related, but hopefully through this talk, you'll see that they're highly related. And I will first begin with a little overview of what we do for our group. And I like to name things after myself before this talk. So I named my group the Polo Club of Data Science. And at the bottom, so all of my students, current students, and recently graduate students. And at the core, what we've been working on is how to combine two kind of intelligence, if you would. One is the AI, these days very big, and then also the human intelligence side of things. So you can think of it more about how the scalable automated methods and also the flexibility of human being. And the goal there is to develop scalable interactive tools to make sense of large-scale data set and model. So these days I argue that these are essential for any kind of analysis that we want to do. And there's a number of research thrusts that we have at Georgia Tech. And so 5 of them, I summarized them. One is human-centered AI, how do people interact with AI systems, how to make it easier. Security, we have been working in a long time in the cybersecurity, but these days we also care about security of AI, which is why I have adversarial machine learning. And starting with my PhD and also some of my students have been working on large graph mining, graph data, network kind of data, how to visualize them, and also application in social good and health, and of course also security as well. So today we're going to focus more on 2 of them, particularly how to make AI secure, how to do, for example, look at the defense, protection of AI, and also relatedly, how to make them more interpretable. So why do we focus on them, or how are they related? Right? So for the secure AI part, I think I don't need to convince you too much, because now AI is often used in safety critical applications. So it's very important that we study the threat and countermeasure. Right? So you have probably already seen probably a lot more than you would want examples and the news that all these accidents. And people don't really fully know until after a lot of investigation, and sometimes even after investigation, you still don't really fully know. So that kind of bring us to the need to really go deeper into understanding. When you say you have like an accident, or maybe you say someone say, now you have a protection, you can actually help avoid those accidents. How does that really work? Right? So, and as you would know, like these days, often AI, when people mention AI, often they think about black boxes, and especially these days because AI often kind of mean using deep model or deep learning models. And often used as black box, not really that good. Right, so ideally, instead is we want to open the black box a little bit, maybe not fully, maybe too much details, but at least make it easier for people to understand what is really happening. And when something goes wrong, really know how to fix it. So, and our way of doing it is through scalable interactive user interfaces. You cannot just say, let's just tell you all the details. You need to provide the right interface to help people understand these complex, large-scale systems. So that brings us to our today's agenda. So for each of these 2 big topics, secure AI, interpretable AI, I will give you a few examples of projects that we have been working on recently, I'm really excited about, and also, of course, some of the latest work that try to start to combine these 2. So I'll start with the secure AI side. So we'll talk about some of the recent work that we do, both on the attack and defense side of AI. And you may say, why do we need to study attack? The reason is that if we want to develop strong defenses, we need to know how the bad guy thinks. So that's why I also be the bad guy and think about how to do the attack. So we'll give 2 examples. One's called Shapeshifter and Shield. Both of them are with Intel, pretty recent Intel collaboration. And then in the second subsection, I will focus on 2 systems. One is called Adagio and MLexploit. So those are tools that make researchers, students, practitioners more easily able to test these attack and defense methods. If you have been working in the area, you notice there are a lot of interest recently. That also means a lot of work both on attack and defense. So how do you allow people to easily test all these attack and defense instead of them kind of writing everything from scratch? So for that, we'll show you 2 examples. And on the Interpretable AI side, we'll talk about some of the recent collaboration with Facebook, for example, developing an activist system that help them, Facebook scientists, understand the models and data sets. And also very recently with Google, we developed GangLab to help people understand this generative adversarial network. So very hot kind of deep learning models, but also very, very hard to train and understand even an expert. So we'll look at how do we do that. And then lastly, we'll wrap up with kind of more high level, like a survey of the state of the art, and also work that my student did with Microsoft research last summer. Yeah. So to start with the secure AI side, so specifically the attack and defense. So begin with a cartoon. So you might have seen it. Is that in the not so distant future, everything becomes smart, including a toaster. So toaster got hacked and thinking it's a blender. And you may say, oh, okay, well, that's just making it up. But it turned out that's true. So you have smart toaster, can smart anything you want. And actually, and all these devices, anything you can imagine now is just having all these, some kind of learning capability or AI in it. So AI security is becoming increasingly important. And there's a lot of these numbers, and from the popular press, you probably have seen that there's just more and more of them, and a lot even more. And also that unavoidably or naturally, say that AI now is also used in safety critical application where the stake is really high. So what our goal is to study when they might break down, like vulnerabilities, and also then develop secure method or AI methods for these high stake problems. Right? So I'll give you some examples, like as I said, the first 2 collaboration with Intel. The first one is about attack. Called shapeshifter attack, how to launch some physically realizable attack. And then the second one called shield is for defense. So we start with the first one, so attack. And it was published pretty recently at PKD 2018, and is, as I mentioned, in collaboration with Intel. And this is also the very first we call targeted physical attack on object detection. So there's quite a number of technical terms here. So what does that mean? Right? So often when people study adversarial machine learning problems, as in a machine learning model want to attack it, what does it really do? Often it's image-based, so as in attacking an image classifier, and where the usual task is you have an image, and then even though there might be many things in it, but you just want one single label. For example, for this image you're looking at, you say, oh, okay, the label is probably a car. But for the human being, that may not really make sense, right? If this is really a part of a larger image, you will see that, well, there's not really only a car. There's also people, there's buildings, so why don't we also label those things? So that's inherent some ambiguity there. So on the other hand, if you're studying this as an object detection problem, well, then it's probably more matching what people were really thinking when they're looking at an image. Well, not only a car, but also have people, all these things, as a building and so on. So what that means is when you're doing object detection, it's very different from image classification. It's trying to recognize and localize multiple objects at the same time. Right? So that's an important distinction between there, because our attack is to attack these object detector. So meaning attacking the machine learning model that can do these recognition and localization. So we'll break that, not just like one image and then change the label. Right? So a little bit of prior information in case you're not familiar with adversarial machine learning. So now it's pretty well established that not just machine learning model, but just even deep neural network models are very vulnerable. You might have seen many of these examples, as in an image, let's say an image of stop sign, and you can change the pixels in some very humanly imperceptible way, like change it, make it a little slightly darker, slightly brighter, and that would get misclassified. Do whatever you want, actually. So in this case, again, misclassify into a speed limit sign. And very easy to do digitally. But it turned out that, well, because a lot of work is done in research academia, so we often come up with what I call like pretty impractical threat model, as in we assume the bad guy know a lot of information about the system. So as in, to do this, they will assume the bad guys know everything. They know how the model parameters, they have access to data and everything. But in practice, you will imagine, well, the bad guys may not know as much information, or maybe much harder to do it. For example, if you are building a self-driving car and you want your car to be able to recognize stop sign. So think about you building the car. What you would do? Well, you need a system that's able to capture the image by using some called a camera, and then likely you need to process those image or video, and to do recognition, right, and all these. So what's really academic folks have been focusing on is they do what I call the digital attack, as in they assume the bad guy would have access to the whole pipeline. They have access to the data, they have access to the model, they have access to even the pre-processing step. So if you think about it, like all these things are in the autonomous car system, and if I really know about everything, then I probably don't even need to attack the model. I can actually do other things. I can just change the label, and then that's it, right? So, but nonetheless, that's often what we assume the bad guys would know. So what we want to focus on is a more, I would say, maybe more practical kind of threat model, as in called a physically realizable adversarial attack, where we don't really mess with the system. We don't even assume that the bad guys will be able to hack into it. But now instead we manipulate physical environment, as in we maybe do something to the stop sign without really going into the car. So that's the kind of attack that we are interested in looking at. Right? So we hope it's more realistic, and also we want to study can we change the stop sign to whatever we want. So before going into the detail, we'll show you the outcome. It's kind of like doing cooking show, but show you the cooked chicken before we go into the details about the recipe. So this is a short video, and where we have the real stop sign on your left, and then the fake stop sign that our technique, shifted technique, is able to generate. So it's printed out from a printer, and a student, my student, Shang, so he would drive his car closely towards the stop sign, and you'll see that the real stop sign correctly classified almost all the time, and the fake one, as you go closer, and originally it wasn't detected at all, but then as you go closer and closer and become a detected person. It turned out that you can make it to be detected and with anything you want, but that's just to show you an example of how you can do these we call physically realizable attack. You don't really need to hack into the system. You just need to manipulate the environment. So this kind of what we call physical attack is not new. They're not new as in they all have been focusing on attacking image classification, where you give a whole image, you just give one label. For example, there's classes that can full face classification. You can print something like a 3D object and can misclassify, image classifier, or you can doing sticker even on a stop sign. But all these are for image classifier, focusing on attacking physical image classifier. Yes. And some recent work that says, well, if you apply these techniques to attack image classifier, and then now you run your object detector on it, actually those techniques would not be able to fool the object detector. As in here, on the left and on the right, the sticker attack that worked for image classifier could not fool the object detector, and similarly on the right-hand side. So that led us to our technique. I said, well, so how do we attack the object detector? Right. So in particular, we attack a state-of-the-art object detector called faster RCNN. How it works is that they have like an image, and then they try to detect what potential region of the image that might have some object in it. We call figure out the region proposal. So in particular, stage one, generate region proposal. What are the potential regions? For example, around the stop sign, you will see many potential regions. And then each potential region, then it tries to figure out like, oh, what might be in it? So if there's enough region that says, oh, this is probably a stop sign, and all those regions are overlapping, then they say, this is actually a stop sign. So that's also done through what the localization classification step. Right. So that means if you want to attack this object detector, faster RCNN, what are the challenges that would be? One is that because of the step and multiple region proposal, if you want to attack it, it's kind of like attacking an ensemble. Right? If you want to make this stop sign to be mislabeled as, let's say, a person, right? Since there's many overlapping regions, you have to fool all the regions. Just fooling one region is not enough, because the other region will compensate and say, hey, wait, you say it's a person, but I say it's a stop sign, and many of them will say stop sign. Right? So that's one challenge. And second is that since now we're dealing with physical objects, so we need to care about distances, angles, lighting. For example, when there's a cloud that goes past, would it actually break the detection? Right? So all those we need to care about. So how do we solve these? Like our technique is to, well, if we need to fool the whole ensemble, well then so be it. So what we do is then we try to minimize, we're doing the optimization step, right? So a lot of these are based on optimization. So instead of really optimizing for region by region by region, now we are going to optimize over the sum of all the classification losses. So that means now we say, well, a manipulation or changes to the color, we will only accept that change when it's able to, for all the regions, and then we'll accept it. So you say, okay, that makes a lot of sense. Yes, after the fact, yes, it actually took a long time to try that. And the second thing is that we don't just want the stop sign to change to whatever you want, right? So we still want it to look like a stop sign, and to human beings at least. So then what we do is we do a constraint on what are the part that the technique, the shapeshifter technique can change. So in this case, we only perturb the red area. So we leave the stop, the white text there alone. And there's a reason for it. Doing it is because like for color red, using a human perception recognition, and that it's better to, or the human eyes is less sensitive to changes in the darker color. For example, darker red, you can do quite a lot more there, and people still cannot see the changes. So that was the one kind of challenge that we solved. And then there's second challenge, which is these distortions due to real world, right? So, and how do we solve it? So as in like in different environment, different lighting, so how do we account for it? So we adapt the technique called expectation over transformation that was originally applied for the image classification. In this case, we extend it so that it would also work for attacking object detector. So specifically how it works is you can think of it, we try to simulate many of these scenarios where we say we have our adversarially generated stop sign, we overlay it on top of these images, we can do all the rotation, we can do the scaling, you can do the different lighting, similar lighting, and then we run the optimization over many of these simulations. So after doing this, many trials, of course, and then you're able to generate whatever you want. So now, if there's a target class, let's say I want to turn it into a person, sports ball, or even a target that you want. So here you notice that these perturbations are a lot more conspicuous, right? So generally, if we wanted to survive more of these physical perturbation or manipulation, then the pattern would need to be more conspicuous. And if you want to lower it, that's fine. So I'll show you another example, a video of an untargeted attack. And in this case, that means we want the stop sign to disappear. So again, similar setup. So you're driving a car towards the stop sign. And in this case, it would just not be detected at all. Pretty scary. It's only go until the very end that now I pick on a bird. So human eyes from a distance, you can't really tell apart. And this is scary, yes, scary enough that DARPA agreed. So they have a new program called GUARD, Specific Defense on AI, and they highlight shapeshifter as a state-of-the-art attack. So the black one is where they show the video, and the program is centered around including developing defenses for these physically realizable attacks. So there's one. I think we're happy that there's now support for this kind of line of research. And also the lead student, Sha, so he, because also this work is part of his thesis, so we'll be starting as an assistant professor at National Taiwan University in the spring. So even more impact, hopefully, and in his career. So that's about attack. And also want to mention a little bit defense, so that we are not saying, oh, hopeless now. So we only have all the attack, the world is doomed. So there are defenses. So we also work on defenses, including a system called SHIELD. And where the focus here is how to develop practical defense. And you'll notice that a lot of work in our group is very empirical. We want things that works. And for SHIELD, I won the KDD 18 Audience Appreciation Award. Show some pretty nice video, convince people this is an interesting problem study. So SHIELD focus on defense and in particular fast and practical defense. So of course there's a lot of work on attack, a lot of work on defense. Our focus here is we want things that work. And when we say we want things that work, that means we want things that are fast. So we don't want to say, oh, wait forever, and then now you deploy it. So we want things that work in real time at high speed. So you've probably already seen, remember this, right? So currently how we attack these image classifier object detection is to manipulate the image. For example, you have a cat. Typically, if it's correct, then we'll say it's a cat. If it's a dog, it's a dog. And how the attacker devise the perturbation is they take advantage of the gradient information from the model. So once they say, so I know all these how the dog, all the pixels used by the model and they reach the dog, and then through the gradient information, you can say, well, now I change the gradient so that whenever I have the perturbation, those perturbation would be sufficient to change the model output, and now it become the cat. So naturally, that means you ideally want to prevent the attacker from using that gradient information. That's a core idea of SHIELD. Technically, we call stochastic local quantization, or SLQ. A little technical, I'll explain what that means shortly. At the very high level is really try to kind of destroy all the to make the gradient information much harder for the attacker to use, right? So kind of denying their access. And how do we do that? At the high level, we are using JPEG compression. So actually, everyone knows about it, JPEG compression. So how does JPEG compression even come in? So JPEG compression is specifically targeting, everyone has used it, right? You have an image, you want a smaller size, put it on the web. And what it's really doing is removing information. Removing information that people cannot see. Right? So at a pretty high compression level, you can really tell the difference. And we're using it because that's exactly targeting what the bad guy is trying to create for the perturbation, where they say, I'm going to introduce something that human eyes cannot see. Well, if that's the case, then we just use JPEG compression to remove that. And specifically, we don't use it like just one kind of compression level. We use multiple kinds of compression level. For example, lower compression level to high compression level. Here you see a little more artifact, and then there's less artifact. And also, that's where the randomization come in, right? We don't want the attacker to know exactly what level we're using. So then that means for an image, we divide it into blocks. And for each one, kind of randomly use that sample compression level. And together, that still become the overall image, right? So that is the main idea. The SHIELD, you can think of it as the middle part, where you use this real-time compression and to protect the deep neural network. So. And this can be applied to both benign and adversarial image. Actually, we don't even care whether it's good or not. Whatever it is, it just passes through the middle. So if there's an attack, hopefully SHIELD will be able to correct it. If it's already correct, hopefully it doesn't really damage the image content. Right? So at a high level, this is a multi-pronged approach that combines the randomization and ensembling through the many models. And also there's another part that I haven't talked about is model vaccination. So that means you can actually train the model or retrain your model with these JPEG compressed models so that the model JPEG compressed images. So the model is used to seeing these JPEG artifacts. So how well does it work? So if you apply our technique on ResNet 50 model. So the dotted line at the bottom there is when there's no defense, and so the accuracy drops. So vertical axis here is accuracy, and horizontal axis here is perturbation strength. So more to your right, that means there are more changes, more pixel changes. More to your left, less changes. So you see more changes, well, the accuracy drop a lot. Where for SHIELD in orange here, still pretty good. And if you look at individual JPEG level, we see it's not as high as the combination or the ensemble. So techniques here, we're looking at FGSM and IFGSM. So those are some common attack method for manipulating the images. Yeah. And as I mentioned, so we care about practical, how practical it is. So which is why that's all the reason why we pick JPEG. So we'll look at the running time as well, like comparing to other competing methods. For example, you say removing noise, of course. You will think about median filter, you will think about total variation denoising. So JPEG is significantly faster, the orders of magnitude faster, and also doesn't hurt the benign accuracy. So for SHIELD, there's some limitations. So one limitation was that we didn't study what we call an adaptive adversary, as in the bad guy would know our approach, and then they kind of tune their methods, right? So we extended SHIELD to also look at adaptive attack. So usually whenever you look at adaptive attack, that also means the bad guys kind of have all access to your model. So usually you will see the access rate is pretty high. So the gray line here is our original SHIELD model, where you will say that as if all the models, we use like JPEG 20, 40, 60, and 80, right? If all the models are known, then attack success rate is about 60%. But we found that, well, actually we can lower it further by training all these JPEG 20, 60, 80 model from scratch. So don't using information from the other model, and then we can lower that attack success rate even further. So this work just appeared at a KDD 2019 workshop. So the idea of compression not only helpful for images, so you can also apply it on audio as well. So there are now some audio attack. So Adagio is a system where we allow people to apply the defense using compression on audio. So adversarial audio very similar to images, but in this case, it's kind of changing the audio. Like instead of saying openintel.com, now it becomes like openepo.com. Again, you can do whatever you want, but this again is digital attack, so it doesn't really survive. Once you play the video in the wild and then get recorded, actually those noise are gone. Right? So, but we still study it. It's interesting for curiosity, academic reason. So adversary again use a similar gradient information like back propagation to attack the model. Right. And here, we apply compression. So that means whenever you have an audio, you do the compression technique. And here, compression, you can imagine there are different methods to do it. And Adagio here is focusing on developing a usable front end to allow people to upload their own sample audio, and then you can choose whatever tech you want, and also apply whatever defense you may like. And even better, you can play the audio, look at the hear the difference. Right, so the very quick video here, you can say create a card, upload a audio, like a sample audio, and then you can do the transcription, like using deep speech, and that's the correct benign transcription. And now you can choose an attack, right? And then you can choose whatever word you want to change it to, whatever you want. This method often really, really slow, so you need to speed it up. And 20 times, okay. So now you see, okay, it got manipulated to your target, right? And then now they say, okay, so we can apply the defense, MP3, let's say, it's the most common. You can also do AMR and so on. So of course, MP3 is much faster, so you kind of can fix it. Right? So there's a very, very cool way to try it. And this is actually part of what I consider the do-it-yourself adversarial machine learning, as you saw, we already have shapeshifter and shield, and there's actually tons more other techniques. So how do we know which one's working? How do we pit them against each other? So Adagio is one of the example recent work where we want to make it easy for people to do it. And as a bigger effort, we also developed the system now open source is called MLsploit to allow people to try even more. So it's doing interactive experimentation with adversarial machine learning research. So now it's recently open source and presented at Black Hat Asia and recently KDD 19 showcase. And the goal is very high-level goal there is as I explained, so it make it easier for students, practitioners, researchers to try all these. So in the way that we can encapsulate this research as modules, and that hopefully researchers can contribute and also to try pretty easily. Allow easier comparison of attack and defense, and also importantly, we provide a user front end that easy to use, allow people to try these pretty easily. And currently, there are a number of modules, some including Shield, which we just showed, and also have all these attack and defense techniques on images, and also some are on the malware. For example, AVPass is bypassing Android malware. We have like Linux malware, and attack and defense, and so on. So, and at a very high level, a MLsploit would allow the user to upload a sample. That's step one, upload to MLsploit, and then they can choose what they want to try. What an attack, what a defense they want to try, and then they can compare the result. And the architecture, we also try to make it simple because we want researchers to contribute to it. So a web portal as a front end, and then through the RESTful API, they can schedule a lot of these jobs, which are the attack and defense computation that you want to run, which are run on worker instances. And currently, installation is pretty easy, one click almost, and then you can run your attack. So we'll go through in detail. Yeah, so this is a screenshot of how the system will look like. So each row here on your right is what we call a pipeline. So as in if I want to try now techniques, you create a pipeline. You upload the data, you pick what you want to run. Each little box here is one of the operations you want to try. And then you can also see, of course, all the technical details that a research module would output. And most likely now we also want to teach in classes and also have a more impact, worldwide impact. So now it's also integrated into, or being integrated into AI Intel Academy course. Right, so that's for some of the recent project on a secure AI. So not like now to switch gear a little bit to the interpretable AI side. So one thing about all these techniques that I have talked to you so far, I show you some accuracy numbers, right? And I convince you, even video, convince you that they are working. But then the dirty secret is that even for people working on them, they have no idea why they work. So they just, okay, number looks good, it must be working. But they cannot answer you at which part of the model that they are attacking, what's the extent, what's the footprint, how do you stop it? Like when you say you have protection, what is really protecting? So that means for the interpretable AI side, it's really important. You need to know what they're doing so that you can better evaluate. And for that, I will give you a few example work that recently we did with companies like Facebook and Google, and including also Microsoft as well, right? So how to make hopefully these models more interpretable so that people know what's going on. So if you're talking to practitioners, often you don't really need to convince them too much. They are already, because of their job, they're already very interested in knowing how and why AI work, right? And how do we do that? It's easy to say that you want to do, but how do we do that? And the general medium that we use is through scalable interactive visualization. And we think that visual way is a very powerful method to achieve that. And the reason that we would want to do it is that for machine learning, it's great at finding patterns from data, but it's not very easy to digest. And where for visualization, that is a very effective way to amplify humans' connection. So cognition. So it's using our very effective way of identifying patterns. And now in the combination, through interacting with the visualization, then users can incrementally make sense of the AI. So one common perception that people might have when we show visualization, well, you make a pretty picture and then that's it. So not really. So visualization is a medium, and through interacting with the visualization, the user can ask questions. So they see something, and then they want to ask about it, and then you show them some more. So the visualization, so incremental is very important. So we'll show you a few examples of how do we do that. The very first one is work that we did with Facebook and helping their internal data scientists to understand their large-scale model and data set. Right, so ActiVis. And it was published in VIS 2017. VIS is a top visualization conference, and ActiVis is now deployed by Facebook on their machine learning platform. Right, so all the motivation comes from data scientists at Facebook who need the visualization tool to interpret a complex model. So I argue that all of you now at Microsoft, so you probably have those kind of needs like whenever you look at machine learning models. So you want to know, wait, when does it work? When does it not work? When it doesn't work, what's really happening? So practical design challenges, as you could also imagine, like so industry is a lot of deep and wide models, a large data set, and also many features, many different kind of data set. It could be images, text, and so on. And so ActiVis started from a participatory design sessions with a number of researchers and engineers and data scientists. Actually, quite a long-term project, over 11 months. And ActiVis is a quick screenshot showing you. I can show you some video about how it works. And now, after development, so now it can visualize the industry scale model that's used by Facebook. So there are a number of challenges that ActiVis aim to solve. The first, as I mentioned, is that the many model parameters, or large models, right? Large model, so many neurons, so many layers, and they're particularly interested in deep network. So many of them, what do we do about it, right? So the nice thing about talking to practitioners and through the observation, we found that, well, there are many of it, but we don't really need to spend the energy on every single one of them. So in particular, we can find out which are the ones that the practitioners, the researcher care more about, and then just focus on those. Like, so for example, this is a front end, user front end of ActiVis. And what we do is we still provide an overview of the full model, like we call the model architecture overview view. But then we allow users to zoom in to the graph and then pick the one that they're really interested in and drill down to that. Right? So they click on it and then they can show the details at the bottom. Right? So a very simple way, but then that does solve some of the important problem. Right? So instead of overwhelming people with everything, we give them an overview. That's actually a pretty common design technique in human-computer interaction. Overview first, right? Detail, zoom and filter, details on demand. So we're using that here. And the second challenge is about how they are interacting with these models and data. So through talking to data scientists, we also learned that, well, there are many different ways that they want to do the understanding. And at a very high level, we would categorize those as we call instance level understanding and subset level investigation. Instance level here, we mean looking at individual instances. So as in you're doing programming, right? So or you're writing a model, that's when you pass specific individual examples through a data point through it and then look at how it works. So as you imagine, it's very, very helpful for debugging, as in like unit tests, if you would, right? And that's one very common way. The other way, and that the practitioner noticed, is that the instance level is great. It can get a very deep understanding, but it's also not very scalable. This is why there's a subset level, also very common, which is more scalable, as in doing high-level categorization of the data. So it could be, let's say you're doing classification. So that means your subset level would be at the class level, the whole class of image, whole class of dogs, whole class of cat. But then subset, it could also be a smaller granularity, as in if you're looking at human data, you may want to look at, okay, maybe people in certain country, people at certain level, and so on. So you can actually define these subset in different ways. So that means instance level and subset level is actually really covering a spectrum of analysis, all the way down to individual examples, and then all the way up to super high level. So these turn out, as you may expect, to be complementary. So data scientists, researchers, they really want to, they really need to do both, right? So how do we support this in the activist user interface? So at the bottom of the lower left corner of activist is we call the your activation view, right? So here each column is a neuron in this matrix. So each column here, neurons, and each row here, we're actually combining both things. So it could be instances, and also could be classes. For example, the first 6, those are classes, high-level classes. So we're looking at text data, right? So that means we have 6 categories of text. You want to, let's say these are Facebook feeds. So we want to classify them. Is it a feed about description? Is it about entity, about abbreviation, about number, and so on. So each row here is one class. And the dot here is the neuron activation string. So that means for a particular class, let's say for description, so it's activating neuron number 1, 6, and 17, and so on, a lot. So darker, higher level activation. But it's not limited to just the classes, right? So the rows doesn't need to be classes. It can be other things too. It could be user-defined subset. So again, we're looking at text data. So that means you can say, why don't we pull together all the text phrases that contain the word how, right? So that become one row. Or how about all the feeds that contain the word how many? That's another. So that means the user or data scientist in this case can define the subset they're interested in. And again, we can put them into the same matrix, right? And even better, well, no limit ourselves on doing subset, we can even add individual instances. So on the right-hand side, that's the instance view where you can actually click some instances and that get added as additional row to the matrix. Right? So for example, this particular sentence, where is Prince Edward Island? Right? So that's 1994, and then you add it to there as well. And the nice thing about it is really combining, putting everything together, much easier comparison. And you can add a few more, right? And you can have instances, you can have subsets. Subset could be very high level, like classes, or user-defined instances. Right. And the nice thing about doing all those at the same time is that you can now change the sorting order of the column, right, which are the neurons. And it allows you very easily to see, oh, so for some of the correctly classified instances, how well does it match a particular class it's meant to be classified with? And for the one that misclassified now at the very bottom, how are they changed? You just visually can immediately see, oh, the right one, they match really well. For the wrong one, you can actually identify which are the neurons that are contributing to that misclassification. So design-wise here, you will see that we're not using any fancy thing. It's more about the conceptual idea of how do we actually unify everything and combining them in an effective way, doing categorization and doing the right interaction to allow people to add everything in there and also providing the right sorting order. So that's what really aiming to do, as in, well, we don't aim for create things like very fancy, very sophisticated. We actually want people maybe to very easily use it. Right. So the first challenges I mentioned, I don't have screenshot to show, but I also want to mention is about scalability. Like any industry and any company, scalability is very important. Actually, it is one of the first things that the group discussed. So how do we achieve scalability is through a number of techniques. One, definitely we leverage a Facebook computation platform to scale up the matrix computation, which is number 3. And also we do selective precomputation. So through talking to Facebook scientists and also looking at the log data, we know which layers, which neurons are more likely to get used. So that means we can do selective precomputation beforehand. And also each data scientist might care about different things. So that means for each user, they can actually say, oh, I care more about this particular kind of data set, and so that means we can do the user-guided instance sampling as well. So that, again, we can do it beforehand, so that in real time when they have all the model trained, right, this is the internal system, FB Learner, and after they do the training, have all the pre-computation done, they can just do one click and the activists would launch. So Facebook's machine learning platform is used by over 25% of the engineer, so now we make it really easy for them to try activists. So something you might notice is an activist here, we focus on a single model. So it's not very easy to compare multiple models. But in practice, we do want to compare models or even compare data set or compare classes, right? So we'll have this system called Summit that's going to appear in VIS 2019 that help people do the comparison more easily. Class comparison, model comparison, and also we allow people to dig deeper into the model. As in, well, let's say I have a lot of images from ImageNet, 1,000 classes. We know the prediction is white wolf. How do you reach that conclusion in the network that the label is white wolf? So particularly, if you have a whole network that are many, many layers, many neurons, how do we know what are the features, right? In the end, we know it's white wolf, but how do we reach that conclusion? So Summit is the technique and also the system that generate this kind of graph representation to not only tell you, hey, this is the final prediction, but also show you the path and the specific neuron. In this case, could be legs, could be white fur, could be pointy ear, and all these connection and important neurons that contribute to the final one. So in other words, we're creating an attribution graph where you can attribute the final outcome to individual neurons and connection. So I'll show you very briefly a video of how a Summit works. So this is the user interface. In this case, I will show you a scenario where we use Summit and the attribution graph to discover a very interesting, I would say, kind of faulty, but a scenario. So on the right hand, on the right-hand side, that is the attribution graph extracted for a class of images called Tenge. So Tenge is yellowfish. So we know accuracy is pretty high, 92%. But if we look at the features, you will notice there's no fish. There are people. There are a lot of faces, actually. Faces, each neurons. So here showing some example pulled from real data. And then only after maybe closer to the end, then you start to see some fish, right? Some scales, some fish. So that was surprising, and still some people. So actually, maybe that might be a question for the audience. Any guess why there are people in a Tenge class of people feature?
Facebook's data is mostly people.
That's right, again?
Because Facebook's data is mostly just people.
So one guess is because Facebook, the data is from Facebook, so they have people. And
also,
yes.
Pictures of fish are mostly people holding up their fish.
Great guess. So it turned out that yes. So it turned out that Tenge is the kind of fish that you often will want to catch and hold in your arms and then kind of like trophy. You say, oh, okay. It turns out most of it is so that means what you're really detecting, very accurate accuracy, right? So 80% is great. It's really first detecting is the face, is the fingers. If the fingers, okay, then they're good. That is probably tangible. So that's surprising, right? If that leads you to really think about, okay, so detection, just looking at the accuracy, not really sufficient. You want to really know what's happening, right? Because data could change. In the future, you might get new data, do not have people. Then we're going to break, probably, actually. Right? So that was the very quick example, activist and also submit, so they're related to that. And a lot of these models, and often is that all these tools, we build the tools, and then they're already an audience where you could be a data scientist. But often before people become data scientists or work in industry, often they need to learn these things, right? Learn this model, and often we kind of assume that they know about it. But in practice, actually learning this model may not be easy. For example, for a most recent, one of the most recent, very popular kind of network, generative adversarial network, or GAN for short, turned out to be very hard to learn and train even for experts. So we built a tool called GAN Lab in collaboration with Google AI, the pair group specifically based in Cambridge, and to make that learning effort easier. So in other words, we want to help or use visualization, interactive visualization to help with education, machine learning education, right? So there are actually quite a number of recent work on going in that direction. So quite a few, including like TensorFlow Playground and also other earlier work on visualizing neural network. But modern deep learnings are actually quite complex, right? So many layers, many components inside it, and specifically for GAN, generative adversarial network, the one that you probably seen a lot of example, like fake faces that generated, or like this Airbnb doesn't exist, or something like that realistic looking images, but they're actually fake. So this technique is very powerful, great for generating synthetic data for a variety of users, and also for improving AI accuracy, but very, very hard to understand and to train, even for experts. So I'll show you some math. We're not going through the math, but just show you there's some equation there. And now you need to turn all these equations into the actual implementation, and then see them training, putting in data, and so on. Ooh, a lot more harder. So why GAN so hard, right? Besides there's some math, the reason can be attributed to that it's using two competing neural networks. I will show you easy to understand example first, and before going into technical detail. So in particular, using two neural network, one we call the generator and the other the discriminator, to produce the realistic looking data. We call it generator. Think of it as a scenario where we want to make fake builds, right? So generator in GAN would be like a counterfeiter. In the real world, we try to make fake builds. The whole goal is to make realistic looking builds. While the discriminator component is kind of like a police. You want to spot the fake builds, right? So as you imagine, in the beginning, the counterfeiter is not very good. They generate some bill, but they kind of doesn't look like real bill. The police is doing a great job in distinguishing, okay, this must be fake, right? And of course, the police know the real thing, so have access to the green one, the real thing, right? So can tell the difference. And the counterfeiter get caught, and then now I improve. So okay, well, you caught me, I'm going to make the bill better. So, and then at the same time, the police also update themselves, right? Knowing, okay, well, so you're getting better, I'm also getting better. And so you can imagine that this process repeats. So repeat and repeat. So that means in the end, the generator is able to produce this fake bill so well that the police have trouble distinguishing between whether it's good or not. So at that time, this the training can stop. So because now the generator can produce realistic output. Yes, that's a question.
Your police, though, they spot the fake and they get better, but they don't ever, like, the counterfeiters don't phone them up and are like, oh, I got one by you. So they only get, like, some of the data and a highly biased chunk of the data.
That's correct. So the counterfeiter doesn't really actively probe the police and then say, hey, you didn't need to do this. So the police kind of like looking at whatever they have and also comparing to the real thing and kind of update. The internal is actually updating, we call it decision boundary. So the more information they have. But you're right, yes. Yeah. So this is very high level, right? So, but now you can imagine we're not really talking about counterfeiter police, but actually these are two neural networks, right? So that training. And also even from this toy example, you'll see there's quite a few loops, right? Quite a few connections. And those are the interactions that are actually complex or hard for people to understand. So we'll show you shortly. Yes. Why is it hard? So just conceptually, we already know that, well, there is the kind of component interaction conceptual understanding of GAN that might be tricky. The other is the training, right? So iteratively, we show already many iterations, but internally, actually, each of the network, the counterfeiter or generator or discriminator or the police, those are neural networks we need to train at the same time. And the third one, we want this tool, if we're successful, we want it to be accessible by anyone. Right? We don't want it to be a research tool that only few people use it. We want it easily accessible by anyone. So how do we solve all these challenges? Right? So going back to our a scenario, right? So you want to explain this now in a more technical way, right? So that is training, looking at the data. How do we go about it? So the very first thing you might imagine, well, okay, so I have component, we have some builds. So that means we have the models, we have the data. So what kind of data do we visualize to help people understand this? We consider high dimension data, and so using builds and high dimension data. But it turned out that is not really the main problem. It's more about whether we can successfully explain to people the distribution of data. So in this case, how well does the fake data in purple match the real thing? That's more important. So that means we don't really need to go to high dimensional. High dimensional as an images. So that's high dimensional data. Even 2D will be sufficient. Right? So that we can focus more on the main concept, and then at the same time also very easily visualize data distribution. Like 2D, more than enough. So in the version 1 of our tool GANLab, then we have the color coding set right, so 0.1, and also we'll show the animation through training. So the purple one, we'll see that is iteratively become better and better. The real one is what the user want or what you want to generate, and then over many iteration, then the real thing, the fake thing will look like the real thing. Right? So that
that's really interesting. So like during the iterations, it looks like I don't know much about these networks, but
yes.
That there's an overall bias. I can see it in each iteration, like all the points shift to the left or right or something.
Yeah, so there is some randomness also depend on initialization and also iteration. There are also some randomness involved as well. So yeah, so sometimes the actual training will fail. So there, for example, there's something called like mode collapse where it just fail completely, and even Express don't know when mode collapse happened. So which is why it's so tricky. Yes, but data. This is for data part. It seems okay. 2D may be sufficient because a more important thing to explain actually, which is the second part about the interaction. But before that, so we want to look at the individual component. So what do we do about that? So how do we explain the generator? So generator as the component or the neural network that create the fake builds or fake data. So how it really happening in the generator is that it takes some initial random, usually it's random, it doesn't need to be random, but usually people set it random. And then the generator or the counterfeiter would manipulate it and then turn it into something that hopefully looks real. So more technically, you can think of it as giving an input, initialization. Now you do kind of mapping or warping and then change it into your target, right? So in other words, you can probably overlay a grid on top of your input, and then figure out how to each of these grid cell that are manipulated with precision or stretch or scale to the output. Right, that's technically what's really happening. So that means a counterfeiter is actually a function that get updated again and again and again with the goal of changing whatever initialization you have into what you desire, which hopefully is fake but real. And that means we are really creating a manifold. Right. So how do we show this? This is the time that we think animation is really helpful, where we use the animation, the warping in the middle, that the user can selectively replay and play again, so that they know how do a point in the original space get twist and move to the end. So this together forms the visualization for the generator counterfeiter. And similarly, you want to think about discriminator, right? The police. The police is actually easier because police is kind of like a classic classifier. So you can use a heat map, right? You can looking at the distribution, which of the region likely will be classified as real, which would be fake. Right. So now putting together like all these, we know how to visualize real data, fake data as purple, we know how to visualize generator, you know how to visualize discriminator, has a heat map. Now I can overlay all of it into one composite visualization. And then originally we thought, okay, that our job is done. Version 0.5, all done. And then said, well, the only thing left, since neural network, just add in some sliders and it's done, right? So neural network, change the number of layers. This is 0.5. And the reason there's a reason why it's 0.5 because it totally doesn't work. Actually, when we show even experts, they say, okay, it's super confusing. I have no idea what I'm looking at. The main reason, in the end, is because people have this mental model in their head that we are totally not capturing. So what we really want to say is the first slider corresponds to changing something in the generator. Third slider corresponds to something changing the discriminator, but there's no such visualization in 0.5. So that got us to add to, well, that's actually really important to actually capture the flow. You want to have a landmark, a mental anchor in the head so that they know, okay, what is really the generator doing, what's really the discriminator doing, and then we show the composite. So the end, this is what we're showing. We have the fake data, we have manipulation to generator, and there's something that looks real, and all these are updated, so everything combined. So we'll show you a video of how that works. So in this case, the user will say, I want to generate data that looks like a ring, right, realistic, so that becomes what you want. And you can set the parameters, all the parameters interactively for all the network. You can change the learning rate and everything. And then now you can start training. So you press the training, right? And then now you can see the flow of the interaction. You can see how everything get updated, how the generator get updated, become better, how the intermediate sample get updated, become more realistic. You can turn on and off all the layers. Look at all those, and you can here you can play the animation of the manifold, the warping. It's helpful for understanding. You really see how things get twisted, and you can change the parameter on the fly. So one thing about training GAN, if you ever used it, the dirty secret is that it takes forever. So that's why we play 15 times faster. And after 2,000, almost 3,000 iterations, now you get it. So so in the end, it's pretty good. So this is the fake thing, but look really real. Yes. So that's an example of GANLab. And typically, when you are deploying these kind of interactive visualization tool, you often have like a backend. And particularly when you talk to someone who wants to do a visualization for deep learning, they often will think about, okay, wow, we need a pretty beefy, expensive backend, and then the front end is something that you can run in browser, usually JavaScript. But then we think that that's really a problem because that means it's much harder for people to use the tool. So instead, what we do is we leverage a pretty recent development. You can actually do in browser, on laptop, or on device computation using the TensorFlow.js library, which is essentially doing deep learning using JavaScript, and that's accelerated by WebGL. That means using your graphics card if you have one. If it doesn't, then use CPU. So that means now everything is in JavaScript. Well, of course, that also means now everything can just run in your library. And actually, GANLab is very not dangerous. You can just try it on your browser. You can Google or Bing, I should say, GANLab, and then that should come up the first result. Yeah. So fortunately, also went viral. So when we release it, now it has many likes, 2,000 likes, and 800 retweets. So really exciting project. Right. So I think I'm going to wrap up with some of the high-level thinking about, like for the Interpretable AI and also for secure AI. Like so, we'll show you some examples so far about where we are and so where we want to go. Right. So, and if you're interested in visual analytics or visualization, particularly for deep learning, and you've already been working more on the machine learning side, so I highly recommend a pretty recent survey that we did with, I think this is a great service to community, is looking at what human-computer interaction and also visualizing research can do to help people advance this AI research. And the reason I think is like, of course I'm selling to you, but I think it's really nicely written survey, is that it has done a lot of work for you. And particularly it summarized a lot of the recent visualization research using these like 5W and H kind of category. So for example, each paper will tell you like why they're doing visualization, why they're doing the explanation, like what is really explaining. So you get potentially many things you can explain. Like when they are doing this visualization explanation, who are they doing for? Like who in that for? Are they for model users, experts, domains users, developers? How they are doing it? What are the techniques? So all these. And also I summarize some of the key category or say takeaways from analyzing all those like 50, 60 papers. And currently a lot of the tools aim for experts, and so I assume a lot of domain knowledge. But at the same time, they think more and more that their user who might be students, who might be beginners, want to get into the field. They're using these techniques, but they want to gain deeper insight. So we think that it would be really helpful to have tools that design more for beginners and novices. Often due to ease of design, a lot of tools are instance-based analysis. Instance, you may remember, that means looking at individual examples. It's great, easy to design, right? But in practice, especially for industry, often we're analyzing things at scale. So that means we would like to see more work that focusing on scalability. One very nice observation we have is that the community are really working together. So now we have machine learning people working visualization, and we just hope that that will continue, and we believe it will continue. Number 4 is this. I think we need a lot more work. Is the current lack of actionability. That means we're building a lot of tools that help surface some of the problems that people might be seeing from their data and model, but then we don't really tell people how to fix them. So that means it would be even better not only saying, hey, these are the problems, but also say, here's a solution 1, 2, 3 that we want to try. And a fifth thing is really hard to get away with is evaluation. In practice, very hard to evaluate a visualization tool. Main reason is because you need to find all the users, find the right data, find the right task, but it's important. So we need more comment that, yes, it's important, so we need to do more of it. Number 6, tying back to our secure AI focus is that a lot of these tools currently not focusing so much on helping people understand vulnerability of AI, and we think that's a big need, and because of these models are not robust, and we hope that there's some focus that people would have, want to develop. So lastly, I want to point everyone to work coming out from Microsoft, and also from my student Fred Holman, who interned here last summer, working with Rich and Rob and Stephen at MSR, they look at a very important problem, and actually I would say we don't really have a full understanding of is what do data scientists really mean by interpretability? So I've been talking the whole interpretability. If you talk to different people, they give you different answers. Depending on which community you're in. They're going, we're visualizing or explaining the internal. We're looking at the map. We might be looking at input-output mapping. Maybe you're looking at representation visualization. Actually, that's not really an agreed-upon definition. So what the team is doing, they build a system called Gamut. Some of you have seen it already in demo. Is how to build this tool through the tool to figure out what data scientists really need for when they say they want to interpret something. So that means the tool itself is not really the end goal, but using the tool, they want to use it as a design probe to understand interpretability. So that was what they're doing. And there's a lot of very interesting discovery. And particularly, they use a scenario where, let's say, using that tool, and suppose these are the problems that data scientists would like to address. So how do they translate these kind of questions into interpretation capability? So for example, if someone is looking at housing data, they say, why does this house cost this certain amount of money? What are they really looking at? They're actually looking at local instance explanation. Or let's say they are interested in asking what ifs, right? So that's actually the counterfactuals that they want to do. Or if they are really they're asking how do we find similar homes priced similarly, what they're really looking for, the kind of interpretation task they have is actually looking at the nearest neighbor, or what are similar things, right? So these are the kind of capabilities that actually data science is aiming for. So what that really means is take away and is Interpretability, often people talk about it, no well-defined, and it's actually natural. And I'm not sure if we really want to really force it into a one box, very rigid thing. So it's not really a rigid concept. And interpretability is more like a collection of things that you will want to consider. And often when people say they want to interpreting things is really depending on the audience. So depending on if you're a domain user, you might want to know a lot more information, but then you don't want to know the technical details. Right? And the last part I want to emphasize is the interpretation. Often people think of it as, oh, I'm going to show you some visual, like static visual, or like the text, and then my job is done. So through this research with Microsoft research colleagues is that interaction is the key. So actually you can almost impossible to really do interpretation without interactivity. The main reason is because doing interpretation inherently is kind of question and answering. You see some result, you need to probe further. And how do you probe further? If you're static, just like on a piece of paper, you cannot ask those questions. So through interaction, that allows the user to ask those questions, right? Realizing interpretability and also understanding. So that means whenever someone from now on, if you say, oh, okay, so we're doing interpretability explanation, the first thing you want to ask them, do you support interactivity? Do you support question and answering? Right? So, or are you just showing me the result and that's it? Right? So that was work that just published at the CHI 2019. Really, really great, and I look forward to more collaboration with a Microsoft colleague. So I'm going to wrap up. Slightly overrun, or not overrun. No, I'm not overrun. Okay, I'm good on time. So I talk about two categories of research that we have been working on, secure AI and also interpretable AI. So we start to see some connection between them. We're doing a lot more starting this semester. For example, the Summit tool that you've seen creating an attribution graph to can really dig deeper into the techniques. And that's what we plan to do, to apply to on these many attack and defense techniques, so that we really know when someone say, I have a technique, I have a defense method, what is it really protecting? Is it protecting a particular layer, particular component of your network, or not really doing anything, right? So that is where the connection that we have. That was why I say towards secure and interpretable AI. And a lot more work to do, and I think we have some good foundation, and I look forward to all the things that we do and also collaboration that we have with Microsoft colleagues. Yeah, thank you. Thanks. Yes.
More questions?
Yes.
So you had at the beginning you talked about these physical attacks on AI systems.
Yep.
Where like I printed this stop
Yes.
sign that's the background is
Yes.
slightly wonky, but
Yes.
to all of us it's obviously a stop sign.
Yes.
And then you talked about these defenses for what seemed like more of the digital attacks. Have you tried applying them
Yes.
to the physical attack? Right. So if
Yeah.
I take the pictures you took that are physical attacks.
Right.
Then I apply these compression defenses. What happens?
Great question. Great question. The question was whether we tried out defense as a shield defense, compression based on the physical texture to attack the window. We actually did, and the compression, if small compression, it doesn't work. It could not overcome the attack. The reason is that, as you saw in the shapeshifter one, is actually pretty conspicuous. The overall, semantically, you would say that is still like a stop sign, right, as in this one. But then those perturbations are strong enough that compression alone cannot overcome. And so, which is why for the briefly I mentioned for the Topper project, which we're in negotiation. So we hopefully will work on it. That program's purely based on defense. Or focus on defense for this kind of attack, where we will need to explore more than compression. So one idea that we have is to look at how do we incorporate or to add in what human would take for granted, as in we have the sense of like temporal consistency, as in if you're showing a video, right, showing video, driving towards it, you would not expect, like the human being wouldn't expect, well, one frame is a stop sign, the next frame is the person, the next frame is a bird. So that kind of temporal, for example, this would not make sense. Like why would you all of a sudden have a lot of people like kind of floating in the air? So we want to add in some of these into the defense. But to answer your question, the compression alone is not sufficient to overcome that. Yeah. So in practice, we do expect using a combination. We will certainly keep in mind for compression as well, because internal compression often it actually help increase the model accuracy too, because our model currently they are not trained on any compressed images. Yeah.
I'm sorry, I know you had a...
Sorry,
Yeah.
yes.
Okay. This is sort of related to this topic, so if you don't mind. So I'm a previous life I did a lot of steganography and steganalysis work, and so this is hidden information in digital images and in audio as well. And I feel there's a lot of similarities here. And as an electrical engineering perspective, what I'm thinking about is that the compression, at least JPEG, standard JPEG compression, is about cutting off the high frequency DCT components. But where the research was going in steganography was that more effective steganography efforts or algorithms comprise spread spectrum embedding. So they'll embed across low, medium, and high frequencies instead of just worrying about the high frequencies. And then inspired by this question, it seems like the physical thing that you generated actually has a lot of low frequency information, and therefore your compression algorithm didn't defeat it because it's only eliminating the high frequency stuff. And so I don't, finally, the question is, have you thought about spread spectrum sort of adversarial defense?
Yeah, so there, I think one example like related to that is, the audience may have seen it, is there's an image, it's a composite image. If you look really closely, is I think Einstein. If you put it really far away, pick up Marilyn Monroe. So that's using the low frequency and high frequency kind of thing. So yeah, certainly that's in our mind. I think the tricky point, kind of going into why we do interpretation, is because actually right now we don't know why it's doing the detection. We only, it looks like low frequency, but low frequency is exactly how detected how in the model, we don't know. So, but yes, so we do want to look at the kind of frequency spectrum, and also throw in other things too. For example, here, to human beings, you can say, oh, there's a shape, and then there's a text. Right, so a lot of times for this model, they don't even consider that. It's just so end-to-end, throw in the image, stop sign, yes. So yeah, so those are kind of like a semantic meaning, and also like you can say a lower frequency, like component in it. So yeah, certainly we want to do it. So we don't know how yet, but
Okay,
yeah. Yes, and there was
Yes. So actually, I have two questions.
Sure.
One is regarding the GitLab.
Yes.
So like a lot of times the mode collapse happens and it just never converges. But like I don't know if there's any like visual interpretation from like why that would happen. I don't know from that work you guys did. Did you guys try to explain if certain things?
Oh yeah, great question. So we do see that that it happened in interface, but we we still don't know how to explain, because even when we're creating is hard. Because of randomness, I mean, unless we have exactly the same setting, but currently no, we don't know how. We don't know how to explain. Yeah, we talked to some experts on that, Moodle Labs, and one use that they have. Oh yeah, this is great. So I can visualize the kind of progress at least for the particular setting, initialization. I know Moodle Labs is going to happen. But it's very hard to still hard to know what's the full sequence of actions that lead to it. Yeah. So the answer is no, we don't know. Yeah.
Got it.
Yes.
Yeah.
So regarding this, you said that you could use, I assume you can use this lab for data that has higher levels of dimensions, right? So how are you projecting into 2 dimensions here?
Okay. Yeah. So actually currently again, support up to two dimension. So it doesn't go higher. It can do 1D too, but we doesn't go to 2D. The deliberate intentional reason for doing that is that because for 2D is actually already hard enough instead for understanding. So we want to just keep it simpler. So if you want to use for high dimension, you do need to project it down first, dimensional reduction down to 2D, and certainly it will be a lot of information loss, but that's possible. That once you turn to 2D, you can use it.
Any more?
Yes, sure.
Regarding the interpretability tools that you've created, and specifically the one for Facebook.
Yes.
You mentioned that it's mostly for model developers to understand their models, but then what about communicating those models, for example, with product or project managers or UX designers? Are these kind of visualizations or results helpful to communicate models, or is it only for advanced users like model developers?
Great questions. Yeah, for activist tools, so it is mainly for model developers and engineers, if you would. And so for communication, I think this might be too complex, like too many moving parts. So some are certainly helpful for the model developer because, for example, here they would want to see all the individual instances, while for communication, maybe you don't, right? Or maybe you do, but definitely not that many. So activists currently is not for that one. I would imagine if you want to build a more communication tool, then it needs to be significantly simplified, and so to be much more focused, so to be more distilled from this visualization. But currently, activists doesn't support that. Yeah, but
do you know if there are any attempts in the research community to target those kind of audience as opposed to model developers?
Yeah, certainly. I mean, even here at Microsoft Research, like Salima Mershi, for example, I met with, and also Stephen Drucker, which I also have collaborated. That's the mentor of my student, and so they have a lot of human-centered AI effort, and I think now they're focusing a lot on the end user, and also, as I understand it says they're also providing advice to like actual product groups on how to like through the user interface do more of these explanation and communication. Yeah, so yeah, I think that's great work coming out from it, and I read a lot of them. But you will notice a lot of the tools that we develop currently is more geared towards like maybe I wouldn't say expert, but at least like people who know about, familiar with some of the technique. But what we do want to bring it, or to have more of this tool available to novices. For example, like for GangLab, that's the direction that we go to, where it's very accessible. People can play with it. It's great for students. It's already used in some classes, and so there's very, very low barrier entry. So I imagine that would be the kind of direction. Yeah.
What are your favorite JavaScript toolkits these days?
Oh, what's my favorite JavaScript toolkit? I always think JavaScript is an unfortunate coincidence that happened before, which I think is true. Factually, it's true. But then now, of course, all my students are doing Python and JavaScript. So we do use a lot of D3 for the visualization because it's programming, so you can do whatever you want. We do use TensorFlow.js a lot. Recently, whenever we did more scalable using GPU, we do that. And then there's also the library, like more framework, React. We do it. I mean, partially because of Facebook. That's when we got started, and then when we work with Google, they have their own similar things. So so those are the common ones that we use.
Of all the tools you showed us today, are they all open source?
Oh, are they all open source? Yeah, so all of these are open source except Activist and yeah. So Activist is because it's on Facebook. But like Summit is open source. Shapeshifter, actually, if we go to my mouse cursor.
As an industry researcher, let me thank you for all your open source contributions. That's really helpful for the rest of us.
Yeah, no. That we would like to. So all the 4 here are open source. Here, everything except Activist. Even our survey is open source. So you want to add more papers to it? Yes, you can. Yes. Yeah.
Any more questions?
Okay. Thank you.